Hello everyone. In today's class we are going to discuss the number systems. A computer, we normally say that a computer do not use a decimal number systems which humans are used to. There are other number systems apart from the decimal number systems, namely octal number system, hexadecimal number system, decimal number system, and which consists of 0 to 9 digits that a human can understand. In details we are going to discuss, because in this video we are going to measure ourselves on decimal number system much. And then we also have the binary number system, is the number used in digital computers and other digital applications. So to begin with, we have the decimal. And we normally say that as the word decimal, you can take the prefix of deci, which means a tenth, which means something is divided into 10 equal parts. Also, we can think of decade, which means it is 10. So in other words, we say that in deci, these ones are number base 10. So meaning that we have in this number system, we have numbers which are at a range of 10. That is, we have 0, we have 1, we have 2, we have 3, we have 4, we have 5, we have 6, we have 7, we have 8, 9, and 9, and that is the end. So if you count inclusive of 0, between 0 and 9, that is 0 to 9, there are 10 numbers. And every day counting, remember, we engage these numbers. Maybe for example, if you want to write a number like 36, you need to combine 3 and 6. If you want to write a number like 54, you need to combine 5 and 4, meaning that there is no any other number that is above 9 that we are taking. So that's why we normally say that these ones are 10 numbers that we use each and every day. So we can say that the decimal number will take a subscript of 10. That is, a subscript of 10 is used for these numbers. And then the other number that we have, that is the binary, and these ones, as the prefix bi means 2. So these ones are number base 2. It is the subscript of 2 is used for this binary. And here the number base 2, we normally say they only take 2 inputs, that is 0 and 1. 0 and 1. And in typical digital computers, 0 represent the off, while 1 represent the on stage, while 1 represent the on stage. And these, we normally say that this is the language that is understood by the computers and other digital applications. And then we also have the other number system that we have is the octal. And as the word octal, if you remember the octagon, which represents the 8 sides, so we can say that the octal are number base 8. The number base 8, meaning that we have 8 numbers in these number systems that we work with. So we have 0, 1, 2, 3, 4, 5, 6, 7, and that's all. So they take the maximum of 0 to 7 numbers. So that is a number base 8, or the subscript of this number is 8. And then other number system that we have is the hexadecimal. We have the hexadecimal number system, and these, as the word hexa means 6, while decimal, this one means 10. So if we combine the two, we get 16. So meaning that in this type of a number system, we have 16 numbers, that is 0 to 15. And since in the decimal number we have 0 to 9, it means still we have we are remaining to get the other 6, and these other 6, they takes the letters A to F. So meaning if you are to give all the members of this number system, you have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then from 9 we have A, B, C, D, E, F, where A, it takes 10, B takes 11, C takes 12, and then D takes 13, E takes 14, and F takes 15, and F takes 15. So let us convert. So let us have different conversions, and this one we are going to measure ourselves on base 10 to other decimal number system. So, and in this case we are going to use one method which is known as successive division method. And with me I have one example which I have taken 348 as my case. And to do this, we take 348. If you take 348, then you divide it by 2. That is 348, you divide by 2, you get 174 remainder 0. So in one column we are recording our number that we get, and the other side we are also recording the division. So now if you take again 174, you divide by 2, you get 87 remainder 0. So we record the 0 here. And then if you take 187, you divide by 2. Now you are not going to get a remainder of 0, but if you take 87 and then you divide by 2, you get 43.5. So you can take, to get the remainder, you take 0.5, which is remaining after 43, then you multiply by 2, and when you multiply 0.5 by 2, you get a remainder of 1. The same case, if you divide 2 and 43, you get 21 remainder 1, because it is 21.5. So now you take 0.5, you multiply by 2, you get 1. Then if you get 21, you divide by 10, you get 5 remainder 0. The same case. So then in our answer, you will realize that in the last one that we get, this one we take it as the most significant bit, and on top here we have the least significant bit. So now we start taking our answer from the most significant bit to the least significant bit. So now in this case our answer becomes 1 0 1 0 1 1 1 1, then 0 0 base of 2. Remember to include the subscript of that. And then I've decided we take, in the second example, we take the same decimal number, we convert it now to base 8 or octal. So in our previous example, in our successful division, remember we divided by 2 because it was a binary of base 2. Now we are going to divide the same by 8. So if you take 8 and then you divide by 348, you get 43.5. Now you can separate the two, you get 0.5, which will form the part of our remainder. 0.5 you multiply by 8, you get what? A remainder of 4. And then you take the 43, now you divide by 5. This one takes us to 5. If I'm not wrong, 375. Now So we shall take the whole part now. That is where, to get the remainder, you take 0.375, you multiply by 8. And when you multiply this by 8, you get a remainder of 3. And then now, you divide 8 again by 5. In this case, you can see that 8 is more than 5, so it will be a 0, then remainder of 5. Why remainder of 5? Because if you divide the 2, you get 0.6225. And now, if you take 0.625, you multiply by 8, you get a 4. So, in this case, our most significant digit is here. Then moving upward to get our least significant digit. So in this case, our answer becomes 5, 3, 4, base 8. Remember to include always the subscript. Remember always to include the subscript. So in our last example, we are also going to convert 348 to an hexadecimal. So meaning that we are going to take 348, we divide by 348, we divide by 16, and if we divide by 16, we get 21.75. This 21.75, remember to get our remainder part, we are going to get 0.75, we multiply by 16, and if you multiply this by 16, you get 12. So our remainder here is 12. Then still you get 16, you divide 8 by 21. In this case, 16 goes only once to 21. Then we have a remainder of 5, because if you divide the 2, you get around 1.3125. And if you take 0.3125, you multiply by 16, you get 5. And then from there, you can divide 16 divided by 1. Of course, 16 is more than 1, so you get 0, remainder 1, 0, remainder 1. So in this case, remember our most significant digit is here, and on top here we have our least significant digit. And in this case, we will have 1, 5, 12. And remember, 12 is greater than 9, so we need to convert it to its equivalent letter. Remember, we represented from 0 to 9 and then A to F. And if we take this to the equivalent letter, this one becomes 1, 5, then C, base 16. Remember always to include the base, which is 16, to separate different number systems. And that brings us to the end of our number presentation. If you have found it helpful to you, consider subscribing, like, and send it to more, so that it can reach to more and be of benefit to more students. Thank you.